Hey, it's David from Imply. Today we're going to talk about how Apache Druid works. So if you're considering this database, you'll get a really nice overview in terms of how Druid does what it does. And so let's get to it. First of all, why are developers and architects choosing Apache Druid? And it's really the fact that Druid is a fantastic open source database for analyzing event data at scale. And so a typical data flow looks something like this. You have clickstream data or application logs, sensors, telemetry, what have you. That data is generated and then it is ingested into Apache Druid. Druid supports SQL and powers an interactive visualization or some type of automated decisioning workflow. Now, when you look at this visual, you're probably thinking to yourself, can't any analytic database support it? And the reality is that Druid is a unique database, is that it's designed for three core distinct purposes. The first is that if you have an application that needs assurances for very fast query response times in the orders of less than 1 second for query responses that support millions, if not trillions of rows of data, you'd be in great hands for Druid because Druid is just that fast. The second is the need to support high queries per second. And the third is that when you're dealing with real-time data from Apache Kafka and Amazon Kinesis and you need real-time insights, you'd be in good hands with Druid as well. And so let's look at the architecture for Druid. Druid's core architecture is really interesting for a couple of reasons. Now, the first to think about is that Druid is a services-based architecture, which means that all of the processes that make up Druid are running independent of one another. So you have processes for ingestion, processes for querying, and processes for orchestration. This is really good for a couple of reasons. One is that it obviously allows for a level of fault tolerance, that all of the services are running independent, but the other reason is really about scalability. So now we have a lot of customization because running as independent services, you can increase or decrease the amount of ingestion throughput that you need based on the type of ingestion requirements that are coming in the moment. Or you have the ability to dynamically change the amount of resources and CPU that you need to support query processing for example, high queries per second. So a lot of flexibility for developers there. Now, when we actually look at the core architecture for Druid, Druid itself can be deployed on a laptop or it can be deployed at scale on a cluster of distributed nodes that can be up into the thousands of nodes if you wanted. There are three node types to consider when you're looking at Druid. The first is what's referred to as a query node. A query node is really responsible for interacting with the application. And the query node is accepting the query from the application. It's then managing the execution of the query across the entire distributed environment. And then it's responsible for reporting the results set back up into the application. The second node type are what's referred to as the data nodes. And the data nodes are really like the core workers and they're really responsible for the core processing of queries in the Druid cluster. Two core functions. The first is handling the ingestion of data, and the second is really about the processing of data through local storage. And so you have local storage residing within the data nodes, and you have that close coupled with computing power that allows for that coupling and high performance by bringing storage and compute close to each other. The third node type is really the master node, which is responsible for the overall orchestration, the overall governance and availability of the cluster. Now, when you look at this entire distributed environment, there is another dimension that's really important to look at, which is the notion of deep storage. Deep storage plays a really important part in the Druid architecture because it's responsible for a lot of the background data movement across the environment. And so when you look at, for example, scale out, Druid can support the elasticity that you need to easily scale out and add more clusters because it's leveraging deep storage to move data segments across the environment. Deep storage is also really good because it allows for deep persistence so that you can lose the entire Druid cluster and you'd be fine, you wouldn't lose any data. Now, looking at that, there's something actually really interesting to take in consideration is that this is an architecture that's much different than your classical data warehouse architecture. In a classical data warehouse architecture, you have a separation of compute and storage. And that separation of compute and storage is really good for elasticity, but it's not so good for performance because you always have to move your data back into the compute nodes at query time. This architecture gives you the best of both worlds. It gives you the performance of coupling storage and compute in the data nodes for fast processing, but it also provides the elasticity of a cloud data warehouse through the deep storage layer. Now, let's take a quick look at ingestion. Ingestion is a really important element of Druid, as you'll see in a moment. The data that can be ingested into Druid can come across one of two flavors. You can have your streaming data coming from sources like Apache Kafka or Amazon Kinesis, or you can, batch upload data coming from databases directly or data lakes and what have you. Now, I think the most interesting element of ingestion is really what we do with stream-based ingestion, and so we'll talk about that right now. And so when you look at an event streaming platform like Apache Kafka or Amazon Kinesis, Druid does something that's very unique relative to any other database out there, and it's the fact that it was natively built for event stream ingestion. And so if you had, for example, a Kafka topic that looks something like this, Druid natively integrates in with the Kafka topic, and it has its own Kafka indexing service that allows it to manage and track all of the data that's coming into Kafka and then to bring those events one by one into Druid. And so this notion of event-based ingestion is really important because when you're dealing with event streams, data freshness is really important. Limiting latency is really important. So you virtually have no latency on the freshest events that are coming into Druid, but you also have the notion of exactly once semantics that ensure data quality. You also have continuous backup that's built into the architecture for event streaming. And you really have this notion of query on arrival, where you can query the freshest data without having to wait for an entire file to be generated before you can start querying that fresh, hot data. The last dimension of ingestion that's important to look at is the notion of scalability. Kafka and Kinesis, these were built for kind of internet scale, modern day event streaming. And so you can have potentially millions of events per second that are being generated. And if you're trying to do real-time analytics at scale, you got to have that architecture that can scale right alongside it. And that's another great reason for folks using Apache Druid is that it supports the scalability of modern day event streaming. Now, a really cool kind of trick in the back end is that if you don't want to actually store millions of events per second, Druid can support a level of pre-aggregation, which is known as rollup, that can actually reduce the amount of storage that you actually have to utilize depending on the granularity of data that you're actually trying to analyze. Now, ingestion has two parts. Ingestion is really important with getting data in, but ingestion also plays a really important part in terms of the data that's actually being created and how Druid has a special data format that's actually generated, a table that's generated that's very special to Druid that drives the performance of query time performance, and it's really through the ingestion process. So let's actually now talk about what is that data format that's created during the ingestion process. And I think there's no better way to really talk about the data format than to kind of look at a sample data set. And so let's take, for example, since we're talking about Druid is really built for this kind of notion of event data, let's look at a table that has a few kind of key columns. You have a time element. Let's say you have a user element. Let's say you have a click element, whether the person clicked a certain CTA on a web page or not. And then let's look at a duration element for time. I'll change the color, make it a little bit easier to see. And so you have these different column types. And so let's say for time, we'll just put in some timestamps. For the user, we'll put in my name, it's David. We'll put another username, we'll put in Darren. And then we'll put another username, we'll put my name again, David. Let's say I clicked it. Let's say Darren did not click it. And then let's say when I came back to the website, I did not click it. And I spent a minute, he spent 3 minutes, and then I spent 2 minutes on the site. Okay, so now what we're looking at here is a typical example, a very simple example of clickstream data. Now, what's really interesting is that when you think about clickstream data or event data in general, scalability plays a really important part, and that's really a unique aspect of where Druid is so prevalent in the market, is that When folks are looking with event data, they can be dealing with hundreds of dimensions, but they can also be dealing with trillions of rows of data, which then begs the question, how in the world is Druid able to manage so much data at scale? But even more importantly, how can it support aggregations and analytic style queries when you have so much data? And that really comes down to the design philosophy of Druid at its core, which is really about using Druid and having Druid kind of thinking about how to minimize the amount of work. How do you actually analyze less data at query time? How do you leverage the ability to minimize what you need to analyze? And so this really comes down into the data format, because the data format for Druid is highly optimized for analytic queries. And so there's two things I want you to take in consideration. The first is the notion of segments, and the second is the notion of indexing, both of which are automated as part of the ingestion process inside Druid. So what are segments? So segments are Druid files. Druid files that store approximately a few million rows of data, and they're automatically created as data is ingested. And so you have these notions of segments, and you can have potentially millions of segments across your environment. Now, these segments themselves are partitioned by time. And so time plays a really important element with Druid. So every couple million rows, you have a new segment is created, a new segment is created, and so forth. And why do we actually do this? It's really about having the ability to minimize the amount of data that you have to scan at ingestion or at query time. So say, for example, you're trying to execute a where filter based on time over time over the last hour as well as time over the last year, and you want to be able to do some comparative pattern matching recognition. You're going to run a where filter. The where filter against time is really easy with Druid because of the notion of segments and partitioning, because we partition all of these independent files based on a global time index. And so it's very easy for Druid to locate which segments are required for the query. And so it's not having to analyze and scan data in all of the other segments. And that's really important to help drive the performance of the application. The second thing that segments are really good at is this whole notion of high QPS, because we're replicating segments. And by replicating segments, we can ensure high throughput. So if your requirements are for hundreds, if not thousands or more of queries per second, the replication allows for the easy scalability of throughput requirements. Now, one dimension we talked about when it comes to data format is the segment design. The second thing that's important to look at is what's actually happening within the segment. How is Druid storing data in a segment that could help with the performance of queries? And that's where some really interesting things happen, where inside a segment, and we'll represent this by the table above, but as Druid stores each column, it's actually storing each column independently, similar to columnar storage, but it's also storing each column as a separate data structure. And the separate data structure is really important because we do a lot of things with data format to allow for that optimization. And so you look at the columns that we have here, there is a column structure called time. There is also a column type called dimension. And then there is a column type called metrics. And we treat all of these differently. Time is obviously a timestamp, and we know that through the global indexing, we're able to make where filters based on time really fast. What are we doing with dimensions? So dimensions are strings. They can be numerics as well. And dimensions like user ID and click yes or no are really responsible for filters and group bys and aggregations. And and then if you look over at the far right side, metrics are numerics like floating point values and integers that are obviously responsible for calculations and aggregations. Now, what we actually do is really interesting. So we employ a lot of indexes. And indexes they play a really big important part in Druid because it's about minimizing the amount of data that you actually have to analyze and how you drive better CPU efficiency for queries. So for example, when you look at the dimension column type, we have two different indexes that we use. The first is referred to as dictionary encoding, where we'll take every unique value and we'll assign an integer against it. So David gets assigned a value of 0, Darren gets assigned an integer of 1, and then because it's David again, it gets assigned an integer of 0. Clicks, this will be 0, no would be 1, no repeats itself again, so it would be an integer value of 1. Through dictionary encoding, what this means is that at query time, we're not having to read and analyze a string value, but we can actually save a lot of CPU cycles by only having to analyze an integer value. And that actually provides a lot of efficiencies. The other thing that we do that I really find exciting is the notion of bitmap indexing, or also known as inverted indexes. Bitmap indexes will take all of the unique values that exist in a dimension. So let's take, for example, David, and it will create a bitmap in an array based on the unique value of David and where it's located across the entire table. So in this particular case, David shows up in the first row, David does not show up in the second row, and David shows up again on the third row. You can do the same for the value of Darren, and we can create a bitmap index that shows Darren does not show up in the first, Darren does show up on the second row, and Darren does not show up on the third row. Now, this is so exciting, and I think it's actually very fundamental in terms of how Druid is able to drive so much performance at scale. And it's actually as fundamental as columnar storage became over the last 20 years, where columnar storage is really about, isolating the pertinent columns that you need at query time, so you're not having to scan the entire table. What bitmap indexes are doing is it's enabling you to only have to analyze and read the rows that contain the pertinent information. So if you were going to do a where filter user equals David, you can clearly see here that Druid will only have to read rows 1 and 3. And you imagine that at scale, you have a lot of processing efficiencies that get created. So in net here, you really look at the data format, you're really thinking about an optimized data format and the way that Druid stores that data to ensure the best CPU efficiency by minimizing the amount of work and the amount of querying and the amount of data that Druid actually has to analyze under the covers. So which really brings us to our last session, which is really about querying, right? And so how does Druid actually process queries at lightning fast speed and performance? So when we look at querying, there's kind of two core concepts that are important to think about. The first is really the notion of data locality, and the second is really like the algorithms and how Druid does what it does. And so when we think about data locality for a second, and I'm going to go back and kind of draw our core architecture, which shows the query nodes, the data nodes, and deep storage. And we're going to look at this architecture, comparatively, when we think about data locality, is if you look at a different analytics database like Snowflake or BigQuery or any of those kind of core data warehouses, the notion of separating compute and storage means that every time you execute a query, you're going to have to move data from deep storage into your compute nodes, and that's going to introduce network latency, and that's invariably going to slow down the speed and performance of your queries. Druid, on the other hand, takes the segments, and as data gets ingested into Druid using the data nodes for ingestion processing, it will create a segment which will then persist into deep storage, and then we will preload that data into the respective data nodes, and I'll talk about that in a second, which will then pre-populate the data that you need at query time because it's already residing in the data nodes. And this is a really important thing because, again, we're not worrying about moving data at query time. But now the question is, okay, so let's say we're running a query that based on the where filters, it only needs access to segment A. Kind of easy. We look at this architecture and clearly it's this particular node has the segment that's important for us for the query. But now you got to think about doing this at scale. Many folks and companies out there have millions of segments across their Druid environment. So Druid does a lot of optimization and auto balancing on the back end. And that's actually a really intelligent way in terms of how it pre-caches data into the right data nodes. An example for you is think about tiering. Let's take, for example, that if this particular node is the hot node, this is a warm node, this is a cold node, and et cetera, the notion of tiering gives you the flexibility to determine the right ratio of memory to local storage that you need to provide that best balance of price for performance. So as you're ingesting data, Druid has the ability to automatically rebalance your cluster so that you're ensuring the most recent hot data is being utilized in that respective nodes. And then as that data ages, it will move into a different tier. And that all happens in the background without the developer having to know about it. And so the last step for query processing really comes down into how we process data. And that comes down to, for the really fast queries, Druid utilizes what's known as scatter gather, where the core query engine or query node will accept the query from the application. It will fan out and distribute the query to the respective data nodes that contain the segments that are necessary based on the type of where filters and that are being asked for in the queries. And then each data node will be responsible for the partial result set, and then it will send the result back up to the query node. So that's why it's called scatter gather. And then the query node will then be responsible for merging that result set and then presenting it back out to the application. And so taking a step back and kind of looking at this entire architecture, you think about kind of the core purpose of why folks are liking to use Apache Druid. It comes down to really fast performance, the notion of high concurrency, consistent performance under load, and the ability to support real-time ingestion for real-time insights. And you look at this architecture, and there's a lot of stuff happening here that's really exciting. You have a core architecture that's built that's services-based, that allows for the right scalability to right-size your environment for any workload, any scale. You have an architecture that provides the best of both worlds, the speed and performance of co-locating storage and compute, but the elasticity of a data warehouse and separating compute and storage as well. You have real-time ingestion supported through Apache Kafka and Amazon Kinesis, the native integration that we've done there. You have a really fantastic data format, the Druid file format that's designed around segments and indexes that minimize the amount of data that you're actually having to analyze at query time. And then you have scatter gather and the notion of intelligent pre-caching that's ensuring the ability to find the right data quickly and to manage this entire environment and drive really fast performance at scale. And so for those reasons, it's pretty exciting in terms of what Apache Druid has done for so many developers out there across companies at Confluent, Netflix, Salesforce, and so many others. And so with that, I appreciate your time. And if you have any more questions about Apache Druid, please check us out at druid.apache.org. Thanks so much.